Welcome to another video explaining the universe using the particle model. Today's video is titled Physics of the Diode, and I'm basing this on the book that Dave and I have just released. And here is the icon that's we use for our book, and we'll see that here. Yes, the name of the book is Principia Mathematica 2, and the apple represents, a large apple represents Newton's work on gravity at a higher level, what we call level 1, and the smaller apple inside is level 2 gravity that Dave and I worked on with our book. And this is the cover of our book. You can buy the book on Amazon for $34.99. And as I said, I'm starting a new series of videos based on the book. And today's video covers the diode, which is described on page 122, section 7.3.1 of our book. I encourage you to read it because as I go through and give these videos, you'll have already read about it and hopefully will understand my videos better. I've been going through a list of words, and now my new word is magic. These are ones I have done before. Charge was one. This has to do with power distribution, actually. And I'm doing the diode today, and my next one will be on the transistor. I've struggled with these. I'm getting closer on the antenna, I think, to getting an answer, and I'm working on the calculations for the inductor and capacitor. Hasn't quite worked out yet, so they're getting pushed off. And today it's the diode. By the way, Principia Mathematica 2, there is a introductory video that was done on August 21st of 2021, which happened to be my 84th birthday. And you can go to this link and watch that video presentation, which is the introduction to our book. And you can also go purchase the book if you go to this link, www.amazon.com/author/B.D.Hilster, and you can buy it from there. It's just another Amazon link. I will list these in the description so you can copy them and use them whenever you like. Okay, there are a lot of diode types, and I've made videos on many of these, and you can go to my website, particle.guru. But today I'm going to cover the signal diode and the Zener diode. I've covered these others, but this is being covered in the context of the books, that's section 7.3.1. But I'm going to add some more specific information. I'm going to emphasize the physics a little bit and some of the calculations that is not in the book. Try to keep the book a little more simple at the beginning and not too complicated. And so here is the diode, its symbol. It has an anode, and a positive anode, a negative cathode, and if you have a forward bias diode, current flow in this way, reverse bias diode, the current flows the other way. Well, no, the current flows the same way here, diode's reversed. And this is the IV curve. That's I stands for current. Current is on the vertical, voltage is on the horizontal. For the signal diode, the forward bias region, you operate up here. In the reverse bias region, you operate here. And for the Zener, you operate down here. Quite flexible. One curve serving, well, this is really one diode. It's just used in two different ways. And then there's the Zener, which is usually just one way. One of the important points of the of semiconductors is the doping, and silicon is often one of the base materials they use to build a diode or transistor. Germanium is the other. Here's a silicon diode here, all nicely structured, fitting together, and around this center one there's a valence band with 8 electrons orbiting around, being shared with four adjacent ones. And to make an N-type structure in the diode, they infuse phosphorus, and to make a P-type, they use boron. That's only one example, and you don't know. I'm sure that there's degrees of doping. How many they put in affects how it works as well, but you can see that when you put a phosphorus in the middle in place of this one, you end up with an extra electron. That's because phosphorus has 5 outer electrons in the valence band. Silicon only has 4, and so you end up with 9, and this has 8, now you got 9, so there's an extra electron. You put boron in with the silicon, and now you only have 3 here, plus the 4 gives you 7, so you have a missing one, and they call that a hole, and that's for the P-types. So you've got these two structures, and the standard is all about charge. This has got an extra electron making it negative. This has a missing electron making it positive. So the standard explanation of diffusion, it's diffusion that causes an electric field in this diode. Here's the N region and the P region, and free electrons move, leaving holes behind, creating positive donor ions. Positive donor ions, a circle with a plus, and negative acceptor ions, that's a circle with a minus. And they just say it moves. Here it is. There's no applied force to it. It's just they just move on their own somehow, and they move that way. We don't know what force causes them to move. Electrons, which are not attached to the nucleus. Now that's an interesting comment. That's one of the first times I've heard that or read it. My assumption is that the extra free electrons is orbiting, but here it says it's not attached to it. So they're just hanging in space, wondering what to do. I don't think that statement's right, but that's what it says. The electrons, which are not attached to the nucleus of the atom, are free to move when external energy is applied, and these are called free electrons. But so it builds up these positive donor ions here and negative acceptor ions there, creating a depletion layer. And that depletion layer, because you got minus here and you got plus here, creates a voltage. And these things, it just happens. Well, you talk about biasing it so that it's forward biased or reverse biased. Forward biased means it's going to conduct. Current is going to flow. And they have the negative end of the voltage source tied to the negative region. This negative is going to repel, push away the negatives here, making that depletion region smaller, and that makes the voltage gap smaller. And the positive does the same thing on this side. You got positive repelling the positive here, also pushing this smaller. And it's because this depletion region is smaller and the voltage barrier is smaller that the current flows. That's their explanation. Now you can reverse this. They keep the diode in the same orientation, P here and here. Reverse this. Now the plus attracts the negative, expanding the barrier. The negative attracts the positive, expanding this barrier, and now the current does not flow. That's their explanation. But they don't explain the IV curve. It just doesn't happen. Now, in the particle model, as you know, if you've watched any of my videos, we reject the concept of charge. There is no electrostatic push or pull, which I just read to you, they use as a description of how these things move. And electrons do not move from hole to hole. Rather, instead of electrons, we have a G1 particle, which is like an electron with no charge. And the G1 particles are emitted from the battery and flow through the wire and the diode at speed c1. C1 is similar to the speed of light, but it comes from the orbital, when the G1 orbits an atom in the battery and then it gets released, it's already moving at this speed c, and it goes through the wires, it goes through the components and back around, moving at speed c1, which is the orbital speed of the G1 particle. The G1 particles pass easily through the p-type region and only lose a few G1s, and we'll go into that here in a minute. The G1 particles interact more through the n-type region and lose more of the G1s. Okay, so, and the reason that happens, why it moves easily through the p-type versus the n-type, is because of the open space. Not about charge, it's about open space. So you take a silicon wafer and you infuse it with phosphorus, and you're basically got, I mean, these are very equivalent. This one's got 28 nucleons, and this has got 31. It's got 3 more. It's got 2 more. It's got more electrons, more G1s. So with all of that, even though when you add the phosphorus, you're making less space. This is the n-type. You're making less space, and it has more. That's supposed to say G2 mass. It has more mass because you're adding phosphorus, which has more nucleons and more electrons. But when you add boron, you can see physically how, yeah, the nucleus is much smaller than the silicon, but there are a lot fewer electrons here and there. This is the p-type. It has more space and less mass. And less mass is also important. More space, less mass. Now, in the physics of the diode, we're talking about G2 gravity, and hence G2 mass. We're not talking about charge. Now, G1 gravity. The only function for G1 gravity in a circuit with a diode, transistor, or anything else is to make sure the circuit doesn't float away and it stays on the table. But every object is surrounded by G1 particles and G2 particles, and this is what I've drawn here. These are particles, individual particles, coming at the diode from all directions. In the horizontal direction, there's a balance. This is the p-type. It has a lot of open space, and this is the n-type. It has less space. But in any case, it's balanced in the horizontal direction, and so the forces are equal at this line. You have a strong force here, it gets weaker and weaker till this point. You have a strong force here, and it gets weaker and weaker to this. And now here they're equal and opposite at this point, horizontally. That's not that much interest. We got the same thing here. You got the maximum, got a number of G1s coming through here. They get lost going all the way through until there's fewer here, setting up a net force pushing downward. And that's what this F2 is. This is the net force as a result of the difference between the number of G1 particles leaving here and the number entering. And so you have a net force here, and you have an equal net force here. And by the way, the G2 particles, the speed is C2. This is faster than light. It's the orbital of a subatomic atom, and so it's moving very fast. And it's acting gravitationally with the diode. And we're primarily interested in these two forces. Now, what I've added here that isn't in the book is the fact that there is a force field inside the diode. Standard model has a voltage potential. This is G2 gravity inside the diode. And it has a magnitude here at this point, which I represent as a magnitude from a reference point here to a peak here. Same reference point up here to a peak there. And so as the G1s pass through, you lose them, then you have less force. As you're losing them, you get less force. And it drops down until it gets to what I call the equal point. All the forces down here are pushing inward. And that's true here. The forces are pushing inward, but that's the opposite direction. It starts here. The force drops, but not as fast because of the open space, until it hits the PN junction. That's the junction. And then it drops here at the same rate it drops here. And when these two meet, when they're equal, this is a point at which the G2 force internally is equal. So here's what happens. I got one G1 particle, it's moving this way. This force at the surface is high enough that it starts accelerating. It starts accelerating before that, but nonetheless it's accelerating and goes faster and faster and faster until it hits this point. Well, it would do the same thing over here if it was coming this way. It would be going faster and faster and faster until it hit that point. So this is the point of which the G1 particle has its fastest speed. It goes faster and faster and faster. Then that's its maximum. Then it goes slower and slower because this force is pushing the other way. This is one of the key things. This force, this net F2 force, controls the speed, and it turns out that the speed is dependent on the G2 mass of this diode. Now, here's a sequence that is really critical, need to pay attention. Now, I'm going to talk about increasing the number of G1s. Instead of one coming in here, I'm going to have 1,000 come in, and then but when I increase the number of G1s flowing through the diode, it increases the G2 mass. I'll get to that point in a minute. It increases the mass, and it should increase the loss. So if I had 1,000 going in and I increase it by 100, it ought to increase the loss by 100. But an increase of G2 mass, because I'm adding more G1s in here, increases the G2 mass. An increase of the G2 mass increases the force. The increased force causes the speed of the G1s to increase by 10%. The force is going to be increased by 10%. And some of the G1s that should have been lost when we made this statement, they should have been lost, are going to pass through more easily. Let me make a quick analogy. An asteroid coming through at a slow speed through our solar system is more likely to hit a planet than an asteroid that's going faster is more likely to pass through. So the speed of the asteroid, the slower the speed, the more likely it is to hit. The faster the speed, less likely it is. And that's what I'm saying. The increased force causes the speed of the G1s to increase, and some of the ones that should have been lost will pass through. In general, there is an additional loss, but not as much as expected. So here are the key factors. By the doping, they create open space or limited space. In the P-type, it's more open space. In the N-type, it's more limited space. F2 force depends on the G2 mass. Now here's the point. G2 mass is actually all the atoms in the silicon and the phosphorus and the boron. They're made up of N1s, which are the nucleons that are in the nucleus, and they're made up of G1s, which are the orbitals, and they exist in the diode when there are no G1s passing through. The sum of that, their organization and their density and all of that gives you the mass, the G2 mass of that whole diode. You add more G1s, you're not adding, when G1s flow through, they're snaking through, you're adding more G1s, which are going to add to the mass. And so you get an increase of G1s flowing through it, you increase the mass, which increases the force, that increases the speed, and you end up with particles, G1 particles that should have hit and got and escaped and scattered, but don't, because they're going faster, they go through easier. Those are the three key factors. There's another point I want to make. Unfortunately, this will take some time to go into, but the number of G1s flowing through the diode can be estimated. On the work I did based on the DC power to a resistor and 1 amp of current, came up with the conclusion of this equation. If you go to this link, and I'll list it as well in the description, you go to this link, you'll understand how I got this number. It turns out that the product of the volts per G1 times the interaction factor of the resistor is fairly constant at 1.60205 e to the minus 11th. This is amps. I will go into the units here, but it turns out that this is it's not absolute constant. I did a lot of estimating of things here, throwing, well, I think this ought to be this, and this ought to be that. So I'm not. This isn't a solid number, but it's a number I came up with, and it's a number I'm going to use in terms of the flows of G1s through the circuit. So we're going to do the forward bias diode. Forward diode, this is a circuit. The battery is a 5-volt battery. G1s are flowing in this direction, and you got the F2 force. And when it's forward biased, the G1s come into the N region, and then go around. Now, this is the IV curve for the forward bar. This is where it operates, and I picked this operating point. I just put this one, and I put the number 4 here and the number 1 here, saying I'm just saying there's a 1-volt drop across here. If there's a 1-volt drop across here, there's a 4-volt drop across here. So the current through here is 4 volts divided by 1K is 4 milliamps. And I use that equation I just showed you, current divided by 1.6 times 10 to the minus 11th. And you find out that there would have to be 250 million G1s flowing through here to create that. Now, that's just showing you what the curve says, but doesn't tell you how this works. But so let's start down here. We got to start down here at a very few number of G1s being generated. Let's just assume there's a very few number. And what happens is that you increase the G1s down here, it changes, it goes way out. You do a little bit more, it goes out. A little bit more, it goes out. But when you come up here, it doesn't go out as far. Normally you might have expected it to go straight, but somehow, for some reason, it changes and goes that direction. So what happens if you have a small number? You're going to lose This is a small space, so you lose some here. Even though it's accelerating, you lose some here, you lose some here, you lose very little there. And so you have a very little voltage drop initially. As you increase it, as you increase the G1s, then the velocity goes faster, and you, if you increase it by 10%, you expect it to lose 10%, but it doesn't, because of the speed causes it to not lose as much. I'm going to try to explain this a different way. That's kind of difficult to get. This is the one I wanted to show you. If you had no speed up, you would expect that you increase it a little, it goes out a little. You increase it some more, it goes out more. And you would expect it to continue on straight. I drew that line in the other one, but that's what you would expect it to do. But what happens is you increase it, and all of a sudden it starts moving. What I'm saying is that the speed, you've increased it enough that the speed has reached a critical point where it starts missing. It doesn't lose this much. It loses less. And so that's what explains the curve. Why it happens exactly here, that I don't know. All I know is that the only way this curve changes direction and loses less than this, than going way out here, is if the speed increases and they miss and they don't lose as many as you're supposed to. The reverse diode is a similar situation. This is the same circuit. I just flipped it around. It's a 1K resistor, a 5-volt battery. And its operating range is here. By the way, on an original diagram of this had a minus current, and this had a minus voltage. Well, there is no minus current and minus voltage. In the previous one here, the current, the G1s, you got added G1s here, you lose G1s, and you lose G1s here. It's all this direction. And it's the same here. You add the G1s, you lose here, and you lose here. It's the same direction. Nothing really changes. Current, G1 current in this case, is going the same direction, whether it's forward bias or reverse bias. So it's positive current and positive voltage, and the operating range shows that you got 20 microamps of current typically. This is the operating point I picked. It's sitting around 5 volts and 20 microamps of current. If you have 20 microamps of current going into circulating around, in the 1K resistor, you got 20 millivolt drop across here. If you got 5 volts generated here and 20 millivolts lost, and you got something less, 5.998 volts drop across the diode, just slightly less than 5 volts. So that's the operating point. Now you can make this a 10 volt. It'll still be 20 microamps, but the voltage drop will be out here at 10. So that's you can calculate what the voltage drop is based on this 20 microamps, but you can also calculate how many million G1s are there. In this case, you take the 20 microamps divided by 1.6 times 10 to the minus 11th, and there has to be 12.5 million G1 particles going around here. You add some here, you add 50 here, you lose almost 50 here, and you lose 0 or 1 here. And that's the operating range. Speed is not a part of this. Speed comes out here. See this knee, this is like in the knee of the forward bias diode. And the speed is what helps the Zener work. There's no speed here. You're working down here in this range. So well, that's because the current, it's so little, 20 microamps. The other one was in milliamps. This is in microamps. Very little amount of current, so you don't get the speed up. 5-volt Zener diode. You can have 5-volt, 10-volt, 12-volt Zener diodes. What you're looking for is that you put the diode in a reverse bias mode. So you've got the P junction here connected to the negative and coming around. And it maintains 5 volts. Here's 5-volt line, and it's straight. It's surprising how straight these things are. I kind of think in reality is a slope here, but that's the 5-volt. Now, in this case, you have a lot of G1s being generated. The operating point, I just picked this point, 1,000 microamps is 1 milliamp. So I'm assuming there's 1 milliamp of current flowing. I just picked that arbitrarily. 5 volts divided by 1 milliamp by 1K is 1 milliamp or 1,000 microamps. And this is the operating point, and you get a 5-volt drop. So you've got to get the number of G1s up. As you increase the number of G1s, you get a large voltage change for a small amount of current change. But when you finally get past the 20 microamps, you got enough G1s that the force is strong enough that you get a velocity. So what happens here, as you increase the G1s go faster here, but this is wide open in the first place. If it's wide open, a lot of open space, doesn't normally hit very much, but you speed it up, it's even going to hit less. So you lose very, very little here. You start to lose some here, but here you're going to lose a lot. Here you're going to lose a lot. You got a strong force pushing back. This is the N-type, which has very little space. And so the slower, as it goes slower, it hits more. You drop a lot, and that's what keeps this line that way. With 1 milliamp of current, using the equation I developed from the other video, there would be 62.5 million G1s flowing. Forward biased diode was 250 million. Reverse biased was 12.5 million, and this is 62.5 million. That number correlates to 1 amp of current flowing by a point in 1 second. That's how I got that number, and this is like that. It's almost like saying that's how many electrons are actually flowing in that circuit. So is all this magic? Today's physicists rely on charge to explain many things, including the diode, but they do not explain what physical property makes the electron negative, nor the proton positive. Electrons move around due to the EMF force, and there is no explanation of what the EMF force is. EMF says it's a force that moves electrons. Tells you what it does, not what it is. These are magical words to me. Charge, EMF are magical words by physicists. The particle model, on the other hand, suggests that the G1 particle with no charge is the orbital of the atom and moves at speed c1 through the circuit and through the diode. TPM suggests that G2 gravity is the force that pushes the G1 through the circuit. It gains speed as it enters the diode and slows down as it leaves. And by the way, it does the same thing for the resistor, the inductor, the capacitor, and even the copper wire that it goes through. As it enters, it speeds up. As it leaves, it slows down. It is this speed increase and decrease that helps explain the IV curve of the diode. My name is Bob D. Hilster, and I am your particle model guru. If you have any questions, ask Particle. You can send me an email at this email address, or you can click on the bell to leave a message. Thank you for your attention.